Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 8 in Introduction to Machine Learning. Today we will talk about how to train neural networks. In the last lecture we introduced neural networks. So here we will look at a particular type of implementation of the gradient descent algorithm for training neural networks. So the algorithm that we will talk about is backpropagation algorithm. It's an efficient implementation of gradient descent, and it is needed because we have several layers in a neural network, and we are going to do forward calculations anyway. Layer by layer we are going to compute the outputs of every layer and feed them as inputs to the next layer and so forth. So while doing so with a few extra calculations, we can store the information that is needed for computing the gradient for such a large layered and complex function, which is the neural network. So it's nothing but gradient descent, but we save partial derivatives as we go forward, and then we link them back together using chain rule of differentiation when we come back. So just to revise, in neural networks you have an input layer, and the input layer, the size of the input layer or the number of neurons in the input layer is decided by what is your input size, what your input dimension is. So if your input dimension is d, then you have d neurons in the input layer, whereas your output layer is the size of the output layer is decided by the dimension of the output. So if you have a multi-dimensional regression problem, you have n different quantities to predict, then you will have n different outputs. If you have n different classes, probability mass function of n different classes to predict, then also you will have n outputs. You can get away with n minus 1 outputs in that case too, but usually it's easier to just have n outputs. And your final layer activation function will also be decided based on what kind of problem you are solving. So for regression problems, your final layer activation will be linear for regression. That means there will be no activation function, and it will be softmax usually for classification. And then all the other hidden layers that you have. So your input layer has no activation function, it's just passing the inputs, but for hidden layers you have a choice of different activation functions. Popular choices are sigmoid and tanh, and the third one is rectified linear unit. So rectified linear unit is currently the choice that seems to have better properties in terms of training neural networks and getting higher accuracies. But you cannot apply ReLU blindly to the output layer. There you have to see what kind of problem you are solving. So now let's look at how this backpropagation algorithm works. So basically this backpropagation algorithm is based on chain rule of differentiation. So if you have functions nested inside functions, then it is handy to use chain rule of differentiation. So for example, the layers of a neural network, these are functions of a function. So basically you can think of your x as being an input into some layer, and what comes out of that is, let's say, A1, and that A1 is the output of the first layer, and that becomes input to the second layer, and what comes out is A2, activation 2, etc. And all the way it comes, what comes out at the end is let's say AN. Okay, so these all these layers are in series, and what we have is, this is the most the function that is the inside most function, and then it is fed as an input into another function and so forth. So these are functions of functions, and the way you could write that is that your input is being operated upon this function h, and that is your first layer, and what comes out of h is given as an input to the function g, and that is nested, so h is nested inside g. So let's say your complete function f of x is a nested function with g of h of x, right? So it is also written as g with a circle, h with a circle of x. Now let's say if we want to find these derivatives, right? So if we want to find the derivative of f with respect to x, then what we will do is let's introduce some intermediate variables. So let's call h of x as y, let's call g of y, which is g of h of x, right? That is your z, that is your f of x, let's call it z. So your derivative of f with respect to x is nothing but dz by dx, which by chain rule of differentiation is going to be dz of dy and then dy by dx, dz by dy and times dy by dx. So we have and these individual derivatives may be simpler to compute, but when you multiply them together you can compute the derivative of a much more complicated function, and we can simply write this as g dash of y times h dash of x, and at the point where we are computing. So what is this y? Y is the value of h of x at the given input x. Alright. So here's an example. So let's say you have d by dx of sine x square. So we know derivative of sine x, we know derivative of x square. So we are going to basically put this together in chain rule, and in chain rule what we will get is the derivative of the outer function, which is cos of x square, derivative of sine of x square, and then times the derivative of x square, which is 2x. So these two get multiplied, and this is how we get the derivative of a more complex function. So this same concept is going to be applied in neural networks. So before that, let's try to express a neural network as a computational graph. So what is a graph? A graph is a collection of vertices and edges. So the circles and the squares that you see in this figure, these are the vertices, singular would be vertex, and then the arrows that you see, these are the edges, or in this case directed edges, because they go from the tail to the head of the arrow, they don't come back. If there is no arrow, if it is just a single line, then it is called an undirected edge. Here these are directed edges because the information flows in the direction of the arrows. And let's assume we have a two-layer neural network where everything has dimension 1 for convenience, but later on we will see how to expand the dimension so that we can deal with vector derivatives, we can deal with matrices of weights and vectors of biases and so forth. So but for now let's assume that everything is just a scalar. So let's say we have an input x, right, and the neural network is such that you have input x, and then basically we multiply this with weight w1, okay, and then we put it in some function, sigmoid function, but let's just call it f function. We put it inside an f function, and we also add a bias b1 to it. Let me draw this where I have more space. So let's say I have input x and it goes into a function f, right, and into that function f we also have bias b1, or I will have bias b1 as the weight, but I will multiply input 1 with that, and here I have w1 being multiplied, and what comes out of that is multiplied with w2, and then I have 1 multiplied with b2, and this goes into a function, activation function g, and then comes the output, and that output, I want that output to be close to a target value t, right. So that is your entire neural network, a two-layer neural network. Later on we will see what if x is a vector instead of a scalar, what if, and because of that your W is a matrix, because the output of the neural network is also a vector, which is the number of neurons in that layer, and so forth. So the computational graph is going to look like this. So whenever you see a circle, circles are variables, okay, and squares are functions, and then arrow is the flow of information. So here we have xi, and so you can see that no variable goes to a variable, no function goes to a function. A function has to give input, a variable has to give input to a function, and the output is stored in another variable. And then some variables are not named here, so I will just leave them as a question mark, but there are some that are named, and I will show you what those are. And we will use some convention, but before we go to that convention, let us look at the basics. We have the variable x, which is the input, which is being multiplied with weight w, and this is the multiplication function, and once these two are multiplied we get some output, and then we have the addition function in which we add the bias b1, and what we get out is a variable z1. Okay. So here now I want to introduce a convention. I will use Zi for all the outputs of the linear combinations. So let's say once we have the or the affine combination, so basically whenever we have weight times the input plus bias, that output I will call it Zi, I being the layer index, okay, not the input index. I is the layer index, so Z1, Z2, Z3 for layer 1, layer 2, layer 3, etc. And then once that Z goes into the nonlinearity, which could be a sigmoid or a ReLU or a tanh, the output of that nonlinearity we will call that as AI, so A1, A2, A3. Okay. So because this is a two-layer neural network, we don't count the input layer, we just count the hidden layer and the output layer. We will have Z1 and Z2, and we will have A1 and A2. So now this Z is being fed into this nonlinearity F, right? So it's a function, so again it's a square, it's a rectangular box, and then what comes out of that is A1. Now A1, so here is your first layer, so this is your first layer, and this is your second layer. Okay. So the output of the first layer is the input to the second layer. So we have, so this is layer 1 and this is layer 2. Okay. So the operations to the left of this line are all the operations in layer 1 to produce this output A1, which becomes input to the layer 2. Now this input to the layer 2 is now multiplied with weight W2 using this multiplication function, and then an unnamed variable comes out of it, and we add a bias B2 to it, and that is this addition operation, and what we get out of that is Z2, right. So this Z2 is the output of this linear combination of the input to this layer, and then we apply a nonlinearity to it, and what we get out of that is A2. Okay. So this is the output of your neural network, the A2 is the output of your neural network, but the story doesn't end there. We want this A2 to be close to the target variable t. So we put that into a function L, which is the loss function, right. So basically if it is for example if it is a regression problem, we will take A2 minus ti whole squared, which is the mean square error, or we would take if this was sigmoid, then we would take cross entropy loss. So whatever that is, we get this loss function L, and what we get out of that is the loss, right. So now what we want to do is we want to train this neural network. So we want to find the minima of the loss with respect to changing W1, changing W2, changing B1, changing B2. Okay. So we want to compute the derivative of the loss with respect to all four unknowns, which is W1, W2, B1 and B2, right. But for the most complex one, for example, would be computing the derivative with respect to W1. So let's look at how that will happen, and that's where we will use a chain rule. So in this chain rule, this is the linear operation of the first layer, which gives you Z1. So this thing that I have highlighted with the red bracket, that is Z1. Once we get Z1, we give that as an input to F, and what we get out of that is A1. So this bigger bracket is A1, and then A1 is input is multiplied with W2, and we add B2. So this is going to be Z2, and then it is given as an input to G, and what we get out of that is A2. So this is the layered structure of the neural network, and then we put that inside the loss L, right. So that is the final bracket, the final layer. So we are treating loss also as a layer. So now we want to minimize this loss, so we want to go towards the negative side of the gradient. We want to compute the gradient of L with respect to W1. Actually we also want to compute the derivative with respect to W2, with respect to B1, and with respect to B2, but we will skip the other three because it will be obvious how to do that once we look at the most complicated case, which is the derivative with respect to W1. So here we are applying chain rule, and what the chain is basically going backwards from the output, from the final thing that we are computing. So what we are saying is that it's nothing but saying that we will take the partial derivative of the loss with respect to A2, then multiply it with the partial derivative of A2 with respect to Z2, and then partial derivative of Z2 with respect to A1, and then partial derivative of A1 with respect to Z1, and then partial derivative of Z1 with respect to W1. That's basically what we will be doing. So that's nothing more complicated than that. So that is what is reflected here in the chain rule. We have the nearest variable to L, which is A2. We will compute that derivative, and then we will compute the derivative of A2 with respect to Z2, and then dot dot dot. I introduced some dots in case it was not A2 but AL, some large number of layers. Here we have only 2 layers, but what if we had 4 layers or 5 layers? Then this series would have continued, and we would have had then finally we would have del of Z2 with respect to A1, then A1 with respect to Z2, and then Z1 with respect to W1. So this is how we will compute the derivative of the loss with respect to the deepest of weights, which is closest to the inputs. Okay, so you will notice that in this entire chain rule of derivatives, there are 2 types of terms that come again and again for multiple layers or pair of layers, 2 consecutive pairs of layers. So one is the derivative of Zi or Zl, if you are talking about the Lth layer, this should be L, sorry. The derivative of Zl with respect to Al minus 1. So derivative of Z with respect to the output of the previous layer or the input of this layer, and that is going to be Wl. And the second derivative type of derivative you will see is the derivative of, for example, Al with respect to Zl, right, and that is going to be the local derivative of the activation function f dash. Where does that come from, right? So let's look at it carefully. Let's look at this expression, right. In this expression, if you look at the derivative, so if you look at this f, right, inside the f is the z, right, and outside the f is the a. So if we look at del a by del z or del al by del z, del zl, L is the layer number, then that is basically the partial derivative of this f, which is whatever f is. So if it is sigmoid, right, or if it is ReLU, whatever is the point derivative at a particular point of that function, that is basically what del al by del zl is. Okay. Now where does the first thing comes from, where we have del zl by del al minus 1 is wl. So if you look at this particular expression, right, and you take its derivative with respect to a, what is a? A is actually, in this particular case, it is x, okay, which is the output of the previous layer, okay. Or if you look at something that is outside, then this is going to be a for the next layer. So that is being multiplied with the weight of that layer. So when you look at the output of the linear term, this entire term with respect to x, then that is just going to be W1. If we look at the derivative of this entire term with respect to what's the output of f, then we are going to get W2. Okay, so that is how we say that del of ZL by del of AL minus 1 is going to be WL. So now that we know how these partial derivatives are computed, let's look at what is this computation graph is good for. So whenever we use a library to define a neural network, inside that library, like a PyTorch library or TensorFlow library or what used to be Theano library, there is a computational graph forming whenever you are using their own functions, library functions, to define the layers of a neural network. And that computational graph is formed so that precisely so that you can do chain rule without having to think about it, and the library computes the derivatives for you for any function, any nested function. So the way it happens is that once we have defined this computational graph by defining the layers, every time we are computing the output of the neural network using an input x and some values of the weights, we are doing what is called a forward pass. So forward pass is basically just sending the information from input to output. That is basically what forward pass is. So in forward pass, basically your information is flowing this way. So x is being multiplied with w, and whatever comes out of it, we add the bias to it. What we get is z, we give that as an input to a function, and what we get out of that is a, and then we multiply that a with w, and whatever comes out of it, we add the bias b2 to it, and then we get z2. We give that as an input to g, and whatever comes out of it is a2, and this is the output of the neural network. But we also compute the loss, so we compare it against the target value t and put it inside the loss function, and what comes out of it is loss. So we get both t and the loss as the outputs of the neural network. Now that is the complete forward pass, and that we will do for every training sample when we are training the neural network, because we want to compute f. We want to compute both f and f dash. So this forward pass computes your f. F is not this f, but the entire function of the neural network. So basically the forward pass is computing the function, let's say capital F of x, where f is the entire neural network, and the backward pass will compute f dash of x at that given x, at that given value of x. And how will that be computed? So that is basically we are taking the partial derivative of the loss with respect to a2. Now notice that we don't need to compute the partial derivative with respect to t, because t is not varying, t is fixed. Your target variable or the target value is fixed. So we are computing the derivative of loss with respect to a2, and then your g function is fixed. We are computing the partial derivative of a2 with respect to z2 and multiplying this in the chain going backwards. So this partial derivative gets multiplied with this partial derivative, gets multiplied with this partial derivative, and if we are computing the derivative with respect to b2, then we don't need to do that. We just basically compute the derivative of z2 with respect to b2. That is a side step we can take, but I am talking about how to go deeper into the neural network. And then again we will take the partial derivative with respect to z1, and then we will take the partial derivative with respect to w1. So we can take partial derivative with respect to w1 as well as b1. Here also we can take partial derivative with respect to w2. So these are all the partial derivatives that are being computed, and whatever is in the chain gets multiplied, right? So when we are doing the forward pass, at that time itself we can compute the partial derivatives and store them locally. What does that mean? So we know that what is this derivative of z1 with respect to w1? What is that derivative going to be? So that is basically going to be xi. Okay, so here your derivative is xi. What is the derivative of a1 with respect to z1? That is going to be f dash at the value z1. Okay. What is the partial derivative of z2 with respect to a1? That is going to be this w2. Okay. Okay, and what is the partial derivative of A2 with respect to Z2? That is going to be G dash at the value Z2. Okay, and what is the partial derivative of loss with respect to A2? That is going to be whatever is L dash, okay, at the value A2. Okay, so now we can multiply these coming back, but during the forward pass we can store these partial derivatives locally at each node. That what is the so that we can use it while coming back. Okay, so here another thing to notice is that we didn't worry about B2 and W2 and B1, but that can also be done. So what is the partial derivative of Z1 with respect to B1? That is going to be just 1. What is the partial derivative of Z2 with respect to W2? That is just going to be A1. What is the partial derivative of Z2 with respect to B2? That is going to be just 1. Okay, so these are all the partial derivatives that you need for computing the derivative of the loss with respect to W1, with respect to W2, with respect to B1, with respect to B2. Just follow the chain from the loss to the parameter whose partial derivative you are trying to compute and multiply everything coming back. But we compute it and store it locally going forward. So going forward, all we need to do is we need to store the partial derivative of f dash at this point. We need to store the partial derivative of z1 with respect to w1 at this point, which is going to be x1 or xi, and so forth, right. So that's local storage of partial derivatives at those operating points is basically what makes it efficient, makes the gradient descent more efficient. Otherwise, if you have to analytically derive the derivative, then it's going to be very cumbersome, especially for deep neural networks. So the backward pass is basically just the multiplication of locally stored partial derivatives, and that is basically what the backpropagation algorithm is. So Jeffrey Hinton and couple of others have independently come up with this algorithm at different times, basically that we can train neural networks using using chain rule of derivatives, and we can store partial derivatives during the forward pass, so that the backward pass simply amounts to multiplying the derivatives coming back. And we saw how that worked when everything was a scalar, when the input was a scalar, every weight was a scalar, so we had only one neuron in every layer, only one bias in every layer, and so forth. Now what if your inputs are vectors, and consequently your weights are matrices and your biases are also vectors? Then what will happen? So we let's take a look at how that works. And basically what we need to do is we need to introduce a concept called Jacobian, and this Jacobian is useful when you have so it's basically a generalization of a gradient. In gradient you had multiple inputs and a single output, and we were taking the partial derivative of that single output with respect to each of the multiple inputs. Now what if your outputs are also multiple? Then basically we will have to have a matrix of derivatives, of partial derivatives, which will be for each derivative of each output with respect to each of the other input, the partial derivative, and that is going to be the Jacobian matrix. So you can think of neural network as basically these blocks of functions chained together, and you have multiple inputs to one function, and what comes out of it are multiple outputs, which are, what I mean by multiple outputs is, for example, you could have multiple neurons in that layer, which is a hyperparameter of that layer, and that can be chained into another function, and that function may have multiple outputs as well, and then finally we may have multiple outputs as well. So if we take each of these outputs of one layer and take its derivative with respect to each of the inputs of the previous layer or outputs of the previous layer, then we can get a matrix of partial derivatives, which is exactly what Jacobian is. So let's say we have a vectored value function f of x, and it actually has two different dimensions, f1 and f2, which is what is shown here, and x itself has three dimensions, x1, x2 and x3. So basically you have f1 of x1, x2 and x3, and you have f2 of x1 and x2 and x3. right. So now if we take its derivative, so basically then derivative of what with respect to what, so we will basically say that we will take the derivative of one the vector value function with respect to the first input, and then the vectored value function with respect to the second input and with respect to the third input. So these are going to be the columns, and the rows are going to be different dimensions of f. So this is f1, this is f2, and this is going to be x1, x2, and x3. So this we will get a 2 by 3 matrix in this case, where your rows are going to be defined by the dimensions of the output, and your columns are going to be defined by the dimensions of the input. So this is the concept of a Jacobian. Now think about if you have 3 outputs here and you have 4 inputs to this layer, the Jacobian is going to be of what dimension? It is going to have 3 rows and it is going to have 4 columns. And what is that? So basically if you think of this as so let's back up a minute. So between each layer, let's introduce something else, right? So in a neural network, what we will do is we will treat the point-wise nonlinearity as separate from the weight multiplication, right? So what we have is, let's say we have input x, so we have x1, x2, x3, right? And that is being multiplied with weight matrix W1, right? I'm ignoring the bias for now, right? And then what comes out of it is we apply some nonlinearity sigma. So let's say that sigma could be sigmoid or ReLU, and what comes out of that, right? That is multiplied with weight matrix W2, and let's say what we get out of that is some output, and then we can have another sigma and so forth. So this is the general structure of layers being stacked together. So the partial derivative around this block is straightforward because it's a point-wise nonlinearity. However, when we go from here to here, the partial derivative is precisely W itself, right? That's what we saw in the previous part of this lecture. So that the del of ZL divided by del of ZAL minus 1 is precisely WL, right? So now this W itself is that matrix, the Jacobian matrix itself. It can be used as a Jacobian matrix itself for this particular module. So the concept of a Jacobian is also tied to the weights. The Jacobian matrix of this module is precisely the weight matrix. Okay. So now with this you probably have a good idea of how the backpropagation works for even neural networks that have vector outputs, have a vector of neurons in every layer and so forth. Now let's talk about what happens when we string a lot of these layers together, right? So there are certain ambiguities that we have in this neural network that need to be controlled. So the first one is that we can generally scale all the weights and biases of a neural network by a particular factor, and we may not even have a qualitative change in the output. So what I mean by that is, let's say you have Wx plus b, right, and we are taking ReLU of that, right. If I instead take some factor alpha, so alpha w, so long as alpha is greater than 1, alpha Wx plus alpha b, the sign of the expression inside the parenthesis does not change, right. So because the sign does not change qualitatively, whatever gets mapped to 0 versus whatever gets maps to identity of ReLU does not change. So I have this ambiguity that these weights and biases are not unique to get the same function done. So that's number one, point number one, right. So this is less of a problem sometimes in sigmoid, because in sigmoid it is not piecewise linear, it is a continuous curve. So which part of that continuous curve we are operating upon is dependent on the norm of W and B. But be that as it may, this creates a problem. In fact, sometimes if we try to, let's say, normalize the inputs, if we try to make sure that the inputs are not too high and so forth. What will happen is the compensation can come from change in the multiplicative factor or an internal scaling of W and B, and you can still get the same behavior from the neural network. So this points to the issue of trying to control or trying to standardize the weights and the biases in some sense, and basically that leads to the idea of putting some penalty on L2 norm of W. We will come to that in a bit. Basically that helps you with the regularization of the neural network also. The second part of it is that once we string a lot of these modules together, right, we make it a very deep neural network, right. So let's say the inputs are going to the next layer, and so this is your input, and then what comes out is your output Y, right. And so once we do back propagation, we know that there is this factor W that is basically the partial derivative at each point, right, and then there is this string of W's that get multiplied coming back together. So what happens if on an average this multiplication of W is greater than 1 or less than 1. So if it is consistently less than 1, then these gradients coming back will become very, very small, so we can have vanishing gradients. And if this multiplication by W is such that on an average it leads to a larger magnitude, mod of W is greater than 1, then we will have exploding gradients. So we can have exploding or vanishing gradients whenever we have deep neural networks, right. So that is issue number 2. So one is that the biases can be scaled without changing the behavior of the neural network much. Second is that if all the weights are very small, if you initialize them to be very small, obviously all the neural networks are randomly initialized in the beginning. So if your initialization is such that you unnecessarily have very small absolute value of weights or norm of weights, or very large absolute value or norm of weights, then you can have exploding or vanishing gradients for training the neural networks. That means with one step of gradient descent, your weights will become very large or very small, and once they become 0, then you can see that all the derivatives going backwards will be 0. If they are very large, then you will get not a number error. So that's the second problem with neural network. The third problem with neural network is that any time we have NL outputs in one layer and NL plus 1 outputs in the second layer, then basically we will have the multiplication of the two as the number of weights. So that your number of weight keeps increasing quite rapidly as you add neurons into different layers. So you pretty quickly run into a situation where you have more unknowns than the number of training samples for deep neural networks. So that's why a lot of the recent research in the last 10 to 15 years has been in controlling these things so that we can train deeper neural networks without having a very large explosion in the number of weights. We have new techniques for initializing weights. So what is, even if we initialize them randomly, so even if you initialize it using a uniform random variable, pseudo random variable, the range of that is important. That range cannot be too large or too small. So things such as Xavier initialization or Kamenhi initialization, though they have derived formulas for what are the conditions on these gradients coming back for deep neural networks that allow us to decide on the range of even for random initialization of weights. So all these have to be kept in mind, which may not be those big an issue when you have a single hidden layer and you have a shallow neural network, but that is basically pointing towards where the research in neural networks has been for the last 10 years or so. The third type of research is, of course, the structure of the layers. The connectivity of the layers itself is very controlled now with the convolution neural networks and long short-term memories. With long short-term memories so that we can train deeper neural networks. So now let's look at one, now that we know how to compute the gradient of the loss with respect to any of the parameters W1, W2, B1 and B2, let's look at how gradient descent would work, right. So gradient descent, as you all know from the earlier part of this course, is quite simply taking small baby steps towards the negative side of the gradient so that you can reduce the loss. So basically you will have an outer loop, right. So you will have a iteration loop, right. Inside that iteration loop we will have a sample loop. So what does that mean? That the iteration loop will go over all the samples, and within each sample we will compute something, right. So what is in the sample loop? Basically when you are looking at a loss, right, so you are looking at the loss of all the training points x, right, with respect to the all the target values t. So this is also vector and this is a matrix, right. So this is sum over all the individual training points and their targets, right. So your individual training points and your targets, their loss will be in the sample loop. So we will compute L of xi and ti, right. So basically your loss will, you will add up the loss here. So your big L, big loss, okay, is going to be capital L plus L of xi ti. So this is sample loop over I, and this is iteration loop over, let's say, n iterations, right. And we will also compute the derivative. So we will also compute the gradient of L with respect to all the parameters theta, right. So theta is W1, W2, B1 and B2, okay. So this will also be added up. So you will have gradient of L plus gradient of this Li, right, whichever is the one that you computed in the previous step, right. And we will similarly have the entire loss function. So that's what we have, and then once we have computed the entire gradient, then what we will say is that we will update that theta. It's going to be theta previous, okay, and minus eta times this gradient of L theta. What is eta? Eta is the step size or the learning rate, right. So here there are a couple of things to note, right. So before we can update, this is where the update is happening. Before we can update the parameters one time, we have to go through all the samples in the inner loop, right. So if you have 1 million training samples, you have to go through the inner loop 1 million times, and whatever is the complexity of the inner loop times the number of samples, right. That much computations you have to do to get one update, and then you have to do n updates. And what is the breaking condition for n? So either n is some fixed number like 1000, or the gradient does not change. So if you take the mod of del of L, then that is quite small. So if the gradient does not change quite a bit, then that means we have reached a flat region of the loss, and we will stop updating. So one of the two conditions can be used for this vanilla gradient update. What vanilla means? Just plain. That means regular gradient descent, and that is because our loss has this sum structure, and that sum is implemented in the inner loop. So the disadvantage of this is that even for one update we have to go through a lot of iterations. So let's look at this role of step size a little bit more, because that is one of the things that we need to carefully set. So here I am showing two different curves, two different green curves, and let's say these two are two different loss curves, right. So we have curve 1 and we have curve 2. So these two curves share a point, and at that point not only the value of the loss function is the same, but also the gradient of the loss is the same. So that is shown by a common tangent line. So if I take a step size which is eta times the derivative, right, the gradient of L, that step size is going to be the same for both loss functions, but obviously what works for one particular loss function or what works for the other loss function is not the same as what works for the first loss function, right. So both of these have different ideal step sizes. So what is different between them? If their function values is the same and the gradient value is also the same, what is different is their second derivative is not the same, or which is called the Hessian in n dimensional case. So that the Hessian itself is important, or the second derivative is important in finding a good step size, but Hessian is expensive to compute, so we don't directly work with Hessian, rather Hessian inverse in fact. So but suffice it to say that we need two different step sizes for these two different curves. So here's another picture. So let's say we have the same curve. If we have too small of a step size, then we will need many step sizes to find the local minima. If we have too large of a step size, then we might either oscillate from left to the right side of the trough, or we might even increase the loss. And then there is a Goldilocks, or the best step size that is just right, that will find us the local minima in one step, or very quickly with a few iterations. So this step size is decided by the learning rate eta and the gradient multiplied together, but that eta has to be controlled so that we don't have either the situation on the left or the situation on the right. So what is used for that is something called learning rate scheduling. And what happens in that, basically every few iterations we change the learning rate eta, so that either we reduce the learning rate or we increase it, so that we can find good local minimas. The other problem with gradient descent is that we may not even want to have a local minima, we may want to actually escape the local minima and find something which is even lower than the current local minima. So to summarize, we need a good step size, which is not easy to find unless you know the second derivative or you do some sort of second order computation. Okay, we have to do a lot of computations before each update, and we can get stuck in local minima. So for example, let's say if we are in the vicinity of this minima, we will actually get stuck here, whereas we may want to go over this hump and we may want to find the next local minima which is lower than the current local minima. So all these are issues with gradient descent, and some of these can be resolved by using a different version of gradient descent, such as stochastic gradient descent or batch gradient descent. So let's look at what is stochastic gradient descent. So the general algorithm is that stochastically or randomly pick any data point, not all data points. In gradient descent we were looking at all data points, computing all derivatives and adding them up or taking their average. Here we will randomly pick one training point, and then we will do the update right after that training point. So what we have is, we have iteration loop. Now this iteration loop is going to have many iterations, and that's it. We just have an iteration loop, we don't have an inner loop. Inside this iteration loop, we randomly select one training point, okay, out of the n training points. Then for that randomly selected point, compute Li, okay. So compute Li and compute this gradient of theta with respect to Li, not the capital L, not all the entire loss, but loss with respect to just one training point, and then update theta. So theta is going to be theta minus eta of gradient theta Li, that's it. And we keep doing this, hoping that we will hit every training point because we are randomly selecting the training point. Now we will need more updates, right? We are and probably your eta is going to be small, but we are getting updates very quickly. Now what is good for one training point, the update that is good for one training point may not be good for all the other training points taken together. So that's a disadvantage of this method, that it is very greedy and it is working with only one training point at a time. But we are getting updates much quicker. So these are called noisy updates. So sometimes we'll get updates that are overall not good for the loss. Loss I mean capital L, which is the sum of all the small li's, right? So Li, capital L is, let's say, the sum of all Li's or the average of all Li's, which is, and Li is the loss for one training point xi. So here we are not worried about what is capital L, we are only worried about small li's. So what is good for one li may not be good for the capital L overall. So what we are doing is, think about your average loss as some function, right, in terms of in the weight space. What is the x-axis? X-axis is the some weight space and the y-axis is the loss. Now this function, now let's draw it a little bit more complicated. So let's say this function is like this, okay, so it has a local minima. Now for it is made up of an average of different losses for each training point, and those different losses have their own local minimas. Okay, so these different losses are with different colors. So the average of all the colors is the red color. Okay, so let's say the average of all the curves. So here let's say we'll take the average. Okay, we'll divide it by n. So average of all the other losses is the red loss, which is the entire loss, right? And what we are interested in is minimizing the loss for all training points, not for a single training point. Yet we are going to do updates that are based on single training points. And why is that? The reason is that whatever is the local minima for the red curve may not be the local minima for one of the other curves. Okay, so we will not get stuck there. Every time we get stuck there, in the next iteration we'll pick another training point and we'll get unstuck, because that may not be the same local minima for another training point. So we'll keep bouncing around, but hopefully the average behavior of this stochastic bouncing around is that we will settle into the local minima of the average curve. Okay, so we will escape the local or global minima of the average curve. We will escape the local minimas of all the other individual curves that make the average curve. So that is basically the idea behind stochastic gradient descent, that it will help you get updates quicker. You don't have to go through all 1 million training points to get one update, and second, because of this stochasticity, your weights will bounce around the global minima, but as you reduce the learning rate, finally you will start to settle towards the global minima. That is basically the idea of stochastic gradient descent, and that has been proven through by assuming certain things about the smoothness of the loss function, and based on that, mathematically it has been proven that stochastic gradient descent has some nice properties that help you get to the global minima or within a tight band of the global minima. Now the disadvantage of this stochastic gradient descent is that when we compute the function, the loss and the gradient for one training point, we forsake a lot of computing power that is available in modern machines. So especially when you are using GPUs and you have few thousand cores in your GPU, the cores are not sufficiently engaged to compute this loss and the gradient of loss for just one training point. So what do? Instead of we go for something that is in between the vanilla gradient descent and the stochastic gradient descent, and basically that is the de facto method these days for training neural networks, which is the batch gradient descent. So this has basically one loop that is outside, and that loop is for batch formation loop or batch formation block. So in batch formation, let's say if you have 1 million training points, we randomly shuffle them and then we divide them into batches. Okay. and we will compute the gradient for one batch at a time. So we are not computing for one sample at a time, we are not computing for all the samples together, we are doing something in between, we are computing the gradient for one batch at a time. So these are randomly shuffled, so these are already shuffled with all the training points are shuffled anyway, and after that we create the batches. And so batch formation is shuffle training points, okay, and then create batches, divide the training set into batches. Okay. Then we have an outer loop. That outer loop is for epoch loop. One epoch is when you have gone through all the batches, and inside that you have a batch loop when you are going through all the batches. Okay. In the batch loop we are computing L batch Li, where I belongs to batch, this batch. Okay. So let us say J, batch J, alright, and then we are similarly computing del theta of batch, and then we are basically updating the parameters based on the batch. Okay. So we are getting updates after each batch, we do not have to wait until the end of the epoch to get an update, and the randomization comes from the batch creation itself, because of which for what may be minimum for one batch will not be the minimum for the next batch, but overall for all the batches taken together we should be able to escape local minimas, and we should be able to find the global minima using based on this stochastic behavior. So this batch gradient descent, so what is the advantage of the batch gradient descent? The size of the batch is such that you can utilize your entire GPU memory with one batch. So you keep increasing the batch size until you get a memory error, and that is a good batch size usually to start with, and based on that you can train your neural network. Sometimes varying the batch size also helps you escape local minimas. So the batch size itself becomes a hyperparameter in practical cases, that you play with the batch size. Your maximum batch size will be determined. What is a batch size? The number of samples you can fit in a single batch. So this size is a batch size, this is the number of batches. So batch size times number of batches is the total number of training samples. So your batch size is a hyperparameter, but it is the upper cap on the batch size is what can fit in your GPU memory, that doesn't give you out of memory error. So now let us look at how we can speed up gradient descent using the concept of double derivatives, which is the equivalent of that in n dimensions is going to be the Hessian. So quickly revising that if you have a perfect quadratic function ax square plus bx plus c, then we can find its minima in one shot, which is basically going to be minus b by a and minus b by 2a rather. And how that comes is that basically you have this f of x, which is ax square plus bx plus c, your f dash is 2ax plus b, and f double dash is 2a. So if you can see this convex function here, so this blue curve is your convex function, and then we have its first derivative, which is the red line, and it is always positive, right, because it's a convex function, and always positive sloping, sorry. And we have the green line, which is the second derivative, which is positive in this case, which means that it is the second derivative is a constant positive, and for a concave function it is the opposite as seen on the right hand side. So wherever the red line cuts the horizontal line, that is the point where we can find the minima of this function, and c does not matter in that case. So here if we want to do this using gradient descent, then we would need to find a perfect step size, and if we knew the knowledge of 1 over f double dash of x, which is the second derivative, inverse of the second derivative, we could find the minima in one step, right. So here you can see two different curves, the red curve and the blue curve. They have two different equations, right, and basically they have two different a's. They share a point where the tangent is also the same. Obviously the second derivative is different for them, which means that 2a is different for them, which means that the ideal step size is going to be different for them, for the two of them. So the perfect step size for a paraboloid, so let's say if we have ax square plus bx plus c and a is less than 0, we know that the minima lies at minus b by 2a. So your perfect step size is going to be 2ax minus 2ax plus b divided by 2a, which is minus of f dash x divided by f double dash of x. So if you think of this as the gradient, then this is your step size. So your perfect step size is 1 by f double dash of x. So this is the second order method for speeding up gradient descent. In n dimensions, there's no double derivative. What we will have is Hessian. So we will have the Hessian inverse, okay, times the gradient of f. Now this Hessian inverse, if you have 1 million parameters in the neural network, your Hessian is going to be 1 million times squared, right. So it's a square matrix, and inverting that would be will take order order n to the power 3 or n to the power 2.6 operations for inverting this matrix. So that's a very expensive operation, and for non-convex functions which we are after, the functions where the eigenvalues of the Hessian are not always positive, right. In those cases when we have saddle points and such, actually using a second order method actually attracts you towards local saddle points, and that's not the behavior that we want. So we don't use this. What we use is a different method. We use approximations to the Hessian or approximations to the absolute value of these eigenvalues of Hessian that leads to speed up. So let's come to that discussion in a bit. I will talk about one particular method which is momentum, but let's just complete our discussion of a Hessian vector. So this is, let's say, a paraboloid. So here if you look at any particular point, let me change the color so that we can see it better. So let's say we take any particular point. Here we have the gradient is a two-dimensional vector because it has to give you the x direction and the y direction for the largest increase in the function, and their correlation between those two directions, etc., is coded by the Hessian matrix. Okay, so this is the Hessian matrix. So an example of that would be, let's say, if you have a two-dimensional function with x1 and x2, the gradient can be computed as such, and the Hessian can be computed as such, and for a particular value of x1 and x2, we can find what is the second derivative. Here I think the Hessian matrix is constant. That is because it's a perfect paraboloid, so that's why the Hessian matrix is constant. Just like for a parabola, the second derivative is a constant. So now we don't have these perfect paraboloids in the loss function of a neural network. What we have is very complicated shapes. So let me show you an example. This is what is going to be more closer to reality when you look at W1 and W2 as two dimensions and the loss with respect to W1 and W2. We are going to see complicated shapes like this. So one direction is W1, the other direction is, let's say, W2, and what we see is that we are after some global minima, but we have these local peaks like local maximas, we have local saddle points. So what is a saddle point? Basically in one direction it is going down, it is like a maxima, in another direction it is like a minima, just like a saddle on a horse. If you, where your legs go, that's where the saddle is going down, but towards your front and towards your back, the saddle is going up. So in the direction of the back to front of the horse, you are at a local minima, but in the direction of side to side of the horse, you are at a local maxima on the saddle. So the way, now this direction can be, the whole saddle can be rotated with respect to some arbitrary axis W1 and W2. So because you can rotate it, these directions can be combinations of W1 and W2 and not just simply in the W1 direction or the W2 direction. So because of that, we look at eigenvectors of the Hessian matrix and not like individual weights themselves. So if you look at the eigenvectors of the Hessian matrix, the eigenvalues define whether we have a maxima or a minima. Positive eigenvalues means we have a minima in that direction, and negative eigenvalue means we have a minima in that direction. So we can also have some positives and some negatives. That's exactly what a saddle point is. When we have all eigenvalues as positive, then we will get a local minima, and when we have both of them as negative, we will get a local maxima. So here, going back to this slide, this is a local minima. So the trouble usually is not to find the local minima in neural networks. The trouble usually is not that you get stuck at a local minima. The trouble usually is that there are all these other structures in the surface of the loss function in which we get stuck. One of them is this saddle point, right? So in one direction we get, in one direction we have a maxima, in another direction we have a minima, right? So we can get stuck here, especially when we are using a Hessian based computation. Other could be like we have long furrows, so think of like half a pipe, like a drain pipe, right? So in one direction we have almost zero gradient, right? In the other direction, in the transverse direction, we have a minima. So here also we can get stuck here. We don't know whether to go here or whether to go here in that drain, right? So let's say this drain is flat, not like sloping, and so these are the more interesting points. So that's why the point that I'm trying to make is that we are not obsessed with finding the global minima of a neural network. If we can escape saddle points, if we can escape long furrows, that is good enough, and we find a local minima so long as we have done some stochastic behavior around it to test that it is deep enough for local minima, that is usually good enough. And there are certain theoretical results that suggest that usually local minimas are almost as low as within the tight band of the global minima itself. Another important reason to not obsess about global minima is that global minima of what, right? Global minima is a global minima of training data, not of testing data. So when it is global minima of training data, there is no guarantee that it still works well for the testing data. So that's another reason we don't obsess about finding global minima of a neural network with respect to the training data. So now that we know that it is not important to find the global minima, but just escape some local minimas and saddle points and so forth, how can we do slightly better than gradient descent to do that? And this is the final concept of this module, and which is that we will use something called momentum in lieu of the second derivative. We will not use a second derivative, but we will use an easier to compute concept. So otherwise we would have to compute second derivative is not just second derivative, it's a Hessian matrix, and we would have to invert it. So we'd want to avoid that, but we will use momentum. So in momentum, the update is going to be like this, that we will have theta, which is going to be updated by the previous value of theta, okay, minus eta times the gradient of theta, gradient of loss with respect to theta, right? Okay. And we are going to add one of the previous updates. So let's call this now L. So let's call this iteration. Let's call this iteration n. Okay, so iteration n, and this is for iteration n minus 1. Okay, this is the previous weight. Okay. In addition to that, we will add some factor alpha of the previous weight update, which was theta of n minus 1 minus theta of n minus 2. Okay. So notice that the dimension of this, the dimension of this, the dimension of this and the dimension of these all are consistent, which is the number of free parameters in the neural network. All of them are the same. Now, what does this alpha do? This alpha is a constant factor which is between 0 and 1. It belongs to this range 0 and 1. Okay. It cannot be above 1. When you have it above 1, then you will have too much speed up in the direction of previous updates and you will get unstable behavior. If it is below 0, then it will have opposite of the effect of momentum. What is momentum? Something that stays in motion, something that is in motion tends to stay in motion, something that is decelerating is or something that has stopped tends to stay stopped and so forth, right? So it's a similar concept. So basically, let's say if you are in a flat region of a loss curve, okay, so this is loss and this is weight. Okay. If we are in a flat region of a loss curve and we make a small update last time, whereas we should have done a large update to escape, let's say, and find another a better minima. So we want a larger update, but we made a small update because of some reason. So if the previous update and the current update are in the same direction, right? If they are in the same direction, then we are going to keep adding them via factor of alpha, and the next subsequent steps are going to be bigger and bigger, and we will speed up the convergence in that case. On the other hand, if we are in some sort of if we are going too fast, then we have positive gradients, negative gradients and so forth, then these two terms will have opposing signs. So when they have opposing signs, then it has a braking effect on the momentum, or let's say if it is like here, it will have a braking effect and it will try to settle down in this trough as opposed to like shooting out of the trough. So momentum can have either a braking effect when you are bouncing around a lost trough, or it can have a speed up effect when you are in long furrows of the lost trough. So that's how we can speed up the convergence of the neural network. This entire momentum equation can be plugged into batch gradient descent, stochastic gradient descent, or the vanilla gradient descent. A good value of alpha is around like 0.8 or 0.9. Those values work very well, but that again becomes another hyperparameter or something that you play around with in practical terms when you are training a neural network. Other ways, there are other better methods of speeding up convergence, such as Nesterov momentum or RMS prop or ADAM, which are out of scope for this course, but you can read up on them and you can use them as a library call in popular neural network training libraries for different software. With this, we reach the end of this module. So to conclude, basically neural networks, they are a generalization over linear regression or logistic regression by adding more outputs and more layers in the function, and they are trained in the same way as logistic regression or linear regression would be trained using gradient descent, but where the gradient descent is computed more efficiently for large number of layers by storing local gradients and using the chain rule. And the same concepts can be applied here of regularization. So just like we had L2 penalty on weights for logistic regression and linear regression, we also have L2 penalty on neural networks. So basically here we also have minus some lambda by 2 times theta, right? So we can add that as an L2 penalty, gradient of L2 penalty also, plus. Also on the, I'm sorry, it's going to be minus because it's the negative of the gradient. So we can add that also here in gradient descent of neural networks, just like we did for logistic regression and linear regression. And that term in neural network parlance is not called L2 penalty for some reason, it's called weight decay for historical reasons. Weight decay, but it is basically nothing but L2 regularization. Right. L1 regularization is not very well used in neural networks because L1 regularization will turn some of the weights off, make them 0, and we don't know how to interpret that in the neural network, that some of the arrows are missing in the neural network. So we don't usually use L1 penalty, but L2 is quite heavily used, and then this lambda becomes another hyperparameter that you tune when you are training neural networks. With this you can model a whole bunch of nonlinear classification as well as regression functions.